14.6, let's finish this off. We're still on directional derivatives, but we're going to answer this one very interesting question, I think. It's interesting. If you have a surface, z equals f of xy, how do you find the maximum rate of change? So what's the, if you like, what direction should you go to get the steepest hill? And how steep is that hill? And here is the solution. It's all to do with the gradient function. The value of the maximum rate of change, right, is the magnitude of your gradient vector at the given point, because you're interested in the maximum rate of change at one specific point on the surface. So it's simply just the magnitude of the gradient vector. And what is the direction that you need to go to achieve this? The direction that you need to go is just the gradient vector. So you don't need to do anything new, in fact. All you need to do is find the gradient vector and you are good to go. So there are only 3 questions like that. So I'm just going to randomly pick my own. So suppose we have a function x cubed plus 2xy squared plus y. And we are interested in the maximum rate of change at the point 1, 2. So we're being asked what's the maximum rate of change and what direction do you go to achieve that? Well, we start off by finding the gradient function, which is the partial derivative with respect to x and then the partial derivative, with respect to y. And in this case, 3x squared plus 2y squared and nothing, 4xy plus 1. And if I evaluate that vector at the point 1, 2, then this will be the direction of the vector that will achieve the maximum rate of change. So what's that going to be? 3 lots of 1 squared plus 2 lots of 2 squared, 4 lots of 1 times 2, add 1. And that's 2, 4, 8, and that's 3, so that's 11. That's 8 add 1. Boop. There you go. So that's the direction that you will travel to get the maximum rate of change. What is that maximum rate of change? Well, the maximum rate of change is the magnitude of that vector. Which I believe, although don't quote me on that, is the square root of 202. So maximum rate of change is that guy. And the direction of the maximum rate of change is 11, 9. This is a valid answer, but sometimes they want to know the direction as a unit vector. And if they did want to know what it is as a unit vector, wouldn't it essentially be just that? So you'll have to check for WebAssign. If it's happy with the direction being 11, 9, then that's good to go. If it is expecting the answer to be a unit vector, okay, there's lots of flavors of this one. It'll probably be this one or something similar. Is it not remarkably easy to find? On a surface at any given point, what's the steepest hill that you would have to climb? The maximum rate of change. And the maximum rate of change happens at the gradient of the point. And what's the value? You know, how steep is it at that point? It's the magnitude of that gradient vector. So here's my next fella, my second example. Put some trig in for a change. Suppose we have that. Now, you know that this is now a fourth dimensional surface. X, Y, Z, and W. So you can't draw that. You can't really imagine it anymore. Don't you just have to trust the math and think of the in a fourth dimensional world, which we are incapable of thinking or seeing. But in a fourth dimensional world, what would the maximum rate of change look like at some given point, pi upon 2, 0. Well, you find the gradient function, and it's cosine x, negative sine y, and oh, what's the, it's easy to forget things if you don't use them much. What's the derivative, partial derivative of tan z?
Secant squared of z.
No, it's secant squared of z. You got to learn how to speak properly. Oh,
so is it
gee,
zebra or zebra?
how do
you say zebra then?
You say zebra. What's so hard about that? You got to learn how to speak properly. I mean, you know, I'm trying my best, one class at a time, to get you to say Z. Gee, how do the French say Z?
Z.
Okay, guys, am I convincing you?
It's okay. I said it yesterday at work.
We'll work on it. Okay, so back to the question then. If you want to know the direction of the maximum rate of change, so actually you kind of find this first. It's going to be cosine of pi, negative the sine of pi upon 2, and secant squared of 0. Okay, the cosine of pi, hopefully everybody here knows that, negative 1. What's the sine of pi upon 2?
Negative 1 also.
Yeah. And what's secant squared of 0 when it's at home?
0.
Try the other one. Remember, secant is 1 over cos. So just figure out what the cosine is.
Oh, 1.
Square it and make it reciprocal. It's 1. So that's the direction of the maximum rate of change, right? That's the direction you would travel in 4 dimensions if you wanted to make this surface, this 4th dimensional function, increase the quickest or the most. And what's the magnitude of it? It's square root of 3. Are we cool with that that concept? I don't really want to, you know, labour it if it's something that's, yeah, I find a gradient at a point and I get the magnitude of that vector and boom, there's the 2 things you're looking for. Am I okay with saying we're good to go on this? Is there anything you want to go over, or do you feel comfortable with the process?
I think I feel okay with it.
Okay, okay is good for me. I'm just going to show you one question from the homework, which is slightly different. And the slightly different is that it is, I think this is one of those pseudo applications. But let's just pretend that it's a real application. suppose that over a certain region of space, the electrical potential is given by V, I guess that's for voltage. So the voltage at the point X, Y, Z is given by 3x squared minus 5xy plus xyz. Right? So it's basically what a fourth dimensional function, right? Find the rate of change of the potential in a particular direction. Isn't that a direction vector that we did yesterday? Is there anything I need to change in question A before I do my dot product and my gradient thing? Is there anything I should be changing in A to get a directional vector? Look closely at the vector V. Is that the guy I should be using in my dot product?
No, should be using the union vector.
Right. It is so, I have done it myself. It is so easy to forget that when you do directional vectors, shouldn't the direction vector be the unit vector version of itself? If it's already a unit vector, great. If it's theta equals pi over 6, don't you end up with a unit vector, so it's great. But if you end up with a vector 1, 1, 7, 2, 3, 4, don't you have to remember that little extra bit that you need to make sure that the vector that you're using is a unit vector? So in this case, it won't be 1, 1, negative 1. It will be 1 over root 3, 1, 1, negative 1 that you will use. And that's the end of that. Now, part B and C of what we've just done today. In which direction does it change most rapidly? Isn't that just another way of phrasing a maximum rate of change? So to get this answer B, won't you take the gradient of this guy and evaluate it at the point 247? That's got nothing, that bit there, the V bit's got nothing to do with that question. Doesn't even interfere with it. It's going to be the gradient of this function at that given point. And won't the maximum rate of change be the magnitude of the vector you got from B? So in B, you find the gradient at the point 247, and in C, you find the magnitude of that gradient vector, and that's the two guys that you're looking for. Now, if this was a good model, what that would tell us is in 3D space, every single point has got some electrical charge or electrical potential in it, right? And if you pick one particular point, it will tell you in which direction is the greatest increase in the greatest increase in electrical potential. I would guess, because I'm not a physics person, that that might be the direction in which the sparks shoot off, you know, like in a thunderstorm, right? If you have a whole load of electrical energy, it will shoot off in one particular direction, won't it, to try and get earthed? So I'm assuming it would probably shoot off in the direction of the greatest change, right, from high to low, try to balance itself out. And that is the end of that section. So we are now going to return, oops, and we're going to look at what the next section deals with. And the next section has a whole load of writing in it. Wow, that's a lot of writing. So what we're going to be doing, and I'll be bringing this back in a minute, we are going to be looking at how do you find local maximum and minimum values of a function, a 3D function, right? So how do you find a local max and min of a three-dimensional function? So this will come back, but let's start a little bit further back than that. Since I am not much of a drawer, I tend to stick to very simple shapes. Can you imagine that's a surface? Z equals f of x, y. I'm not putting the x, y, and z axes in there, a distraction to me. That point there, physically the top of a hill. So it's very like you're walking along the countryside. Don't you have lots of little hills and valleys, right? The top of a hill is called a local maximum. That seems a reasonable name, isn't it? Like Calc 1 local maximums, right? The top of the curve. Can you imagine this surface? This would be called a local minimum. Now, in Calc 1, won't a local max look like this? And won't a local min look like that? So there is quite a good analogy, isn't there, between two-dimensional local max and min and what a three-dimensional local max and min. Now, you must have seen a shape at least once in your life where the curve looked like that. And at this point here, the shape isn't maximum or a minimum, isn't it? A changeover from a happy face to a sad face. I know it's a while back, but can anybody remember what name we give to a point in the curve with this feature?
Inflection point.
Inflection point is definitely a common name for it. The inflection point allows the changeover to happen not at zero, but at an angle. So when that point there, and I don't know how well I've drawn it, but can you imagine at that point there, it also happens to be horizontal as well. And when it is horizontal, it's got another name, it's called a horizontal point of inflection. So an inflection point is a little bit general. Although that is an example of an inflection point, inflection points can happen at an angle of 30 degrees, whereas a horizontal point of inflection can only happen at a zero derivative, right? At a 0 point. So this is a little bit more specific. What would that look like in 3D? What would that darn thing look like in 3 dimensions? I'm not sure. I'm really not an artist. I don't know if this is helping or hurting our process. Can you imagine a surface that looks like a saddle? And at this point here, we have what's called a saddle point. Now, what's weird about a saddle point, just like here, in a horizontal point of inflection, isn't this side part of a local min and that side is part of a local max? So a horizontal point of inflection is like, it's a little bit of both at the same time, right? In this shape here, if you look at it from this direction, wouldn't that, can you imagine looking side in like this? Wouldn't that point look like a local max? If you look at it from this direction, wouldn't it look like a local min? Do you see that in the 3D world, you can have a point in space called a saddle point, which is neither local max nor min, but has a bit of both in it, just like a horizontal inflection has a bit of both in it. So that when we go looking for 3D functions, we are going to be looking for three things: local max, local min, or saddle point. And that written stuff that's eventually going to come back again will be the algebra that we will use to find where local max and mins are. That's the first step. Find out the coordinates of these points. And then secondly, to find out whether it's a local max, a local min, or a saddle point. Now, way back in Calc 1, there were a number of ways you could find, no, rewind that. There's one way that you find the local max. Don't you find in all three cases where the derivative is 0? Isn't that the location of the local max, local min, or horizontal point of inflection? Isn't that where they happen when the derivative is 0? Great. So that's how you find them, right? You just take the derivative and solve for when is it 0. Now, how do you tell local max, min, inflection? There are a number of different ways, but there's a guy called the second derivative test. This is definitely bringing the cobwebs out of your brain. The second derivative test uses the second derivative of whatever the x coordinate of that point is. So can we just say, for argument's sake, that that was at A? What the second derivative test says is the second derivative positive? Is the second derivative negative? Or is the second derivative 0, right? That's the three things that could happen, right? The second derivative at A is a positive number, it is a negative number, or it is 0. And this might catch you. If it is positive, which one of these three do you get? If the second derivative at A is positive, which one of these three do you get?
It's the minimum, right?
For a positive number, I think you said minimum, right?
Yes.
And it is. And for a negative derivative, you are looking at a local maximum. So this is how you find out. You solve when is the derivative 0. That's how you find these critical numbers. You then do a second derivative test. If the second derivative at A is positive, you have a minimum. If the second derivative of A is negative, you have a maximum. And this is a trick question, so I've warned you, it's a trick question. Suppose the second derivative at A is 0. What do you have?
I want to say an inflection point, but
because I have said it's a trick question, you are you are right not to say that. It might be a point of inflection, but a second derivative equaling 0 is inconclusive. All that means is it could be a max, it could be a local min, it could be a horizontal point of inflection. It will be one of those three things, but we don't know which. And we have to do other methods to find out. Do you know the simplest thing is just to plug it into your TI-84 and look at it? Can't you tell if it's a max or a min or a horizontal point of inflection just by looking at the graph? Now, that is Calc 1. Let's look at how this works in Calc 4. First thing you need to know is where do you get these points? Well, by the way, we call them critical numbers. which is the exact same name that we gave to them in Calc 1. So where do you find these critical numbers? Well, in Calc 1, you solved when is the first derivative equal to 0, right? You found what values of x does the first derivative equal 0. In the 3D world, what you do is you solve that. When is the partial derivative with respect to x equal to 0, and at the same time the partial derivative of z with respect to y equals 0? It's kind of like this, right? A little bit more involved, but it's kind of the same. So you will, when you do this, you will get maybe 3 or 4 points. This is true at the point 1,1, at the point 1,7, and at the point 3,4, right? That's the kind of answer you're going to get. You will have found the critical numbers, and that would be stage 1. Where do you get these points, these critical numbers? You get it by solving that. Now, the second part of that puzzle is, what do we have at each critical number? So what I'm asking here is, let's suppose one of the critical numbers was 1, 2. Do we have a local max? Do we have a local min? Or do we have a saddle point at the point 1, 2? You're going to get one of those 3 things, and the job that we have is to find out which one of those 3 things we've got. Okay, which now brings me to that thing. If you want to find the local max or min or saddle point of a function, you solve when is the derivatives both equal to 0. These are called your critical numbers. Now, the second part is what's happening here. And look at how messy it is. I'll try and break it into stages. You've got a critical number, say at 1, 2. You find the second derivative, partial derivative. If that second partial derivative is negative, just like this guy here, if it is negative, don't jump your gun too far, and this funny little guy here is positive, right? So if both of these are true, then you have a local max. Now this funny little guy here is the second derivative with respect to x times the second derivative with respect to y minus the second derivative x then y all squared. If this entire thing is positive, right, then you are looking at a local max. Now, if the second partial derivative is greater than 0, but this fella is still positive, then you've got a local minimum. And then you got the problem one. If this fella here is 0 or negative, then it's inconclusive. It's a bit like the second derivative is 0, but this ugly thing here, if it's 0 or negative, then you're unsure of what may happen. So how do you find out? You plug it into your calculator, or in our case, our software, and you find out what is going on at that point. You look at the picture and you will probably see a saddle point. The vast majority of the time you will, but it is possible that you may not. It is possible that you may see a local max or min instead. It has happened. I'll give you a very simple example in Calc 1. Do you know if you do the function f of x equals x to the 4? Right. If you solve that question, you'll find it's got a critical number at x equals 0. Isn't its derivative also 0? Its second derivative is also 0. Yet you have a local minimum. But if you tried f of x equals x cubed, don't you now have a horizontal point of inflection to see that the information's the same, but what you get at the point 0 is different? So when you have this fella, you've got to make sure that you check it out. Now, I'm going to move this guy over here. And I'll come back. This page isn't going to go away, so don't worry if you haven't copied it all down. In fact, if you don't like copying things down, some people just take a picture of it. Other people wait till I put the video online and go and look at the video and pause it, and then they can write it down as, you know, when they feel like it. I want to show you how we deal with we don't know what's going on situation, right? Where this guy called d of xy, the discriminant of xy, doesn't quite work for us. Where darn am I going? Okay, I'm going to go here. That's not what I want. Okay, let me figure out what the heck's not happening here. You can just bear with me for a few seconds. I'm having issues. One of my pages disappeared on me. I'm now going to get it back. There we go. Okay. Cut this guy in. Let's share that screen with you now that it exists. There we are. Okay, so you should be looking at, well, this is what mine looks like. Let's show you what yours looks like. Yeah, that's what your Canvas page looks like. Great. I said earlier, look, if you want to find a link to this week's class meetings, you click on that guy there and see there's your link, right? That's side issue. Now I want to do, oh, do I want this one? I don't know, I'll try this one first, see if it's going to work nice. Okay, this will work. So you type in your function. So let's suppose it was 3 take away x to the 4 plus 2x squared. What else? Take away y squared. Now, if I click off this, okay, let's shrink this darn thing back a little bit. Now, do you see what's called a saddle point here? If I rotate it, now it's a bit hard to see in orientation, but can you see here that it is a minimum looking thing? Agreed? But if I rotated it this way and this was a little bit translucent, can you see that it's also maximum? I think a saddle point's a good name for it. Doesn't it look like a saddle? So at that point there, that would be one of your 3 critical numbers. Now, if I'm looking at this shape here, wouldn't this be a local max and this would be a local max? Agreed? Let me see if I can try that function with calcplot. That was calcplot I just did, wasn't it? Yes. Let me see if I can do it with GeoBra. Okay, so if I do Z equals X squared plus Y squared. There, can you see a really baby local minimum at 0, 0? Pretty obvious local minimums. You can see what they look like, bottom hills. Right, if I, how am I going to make this go the other way if I stick a negative in front of it? There, well, there we go. A bit crude, but can you see that's what a local maximum looks like? Right. Now, make a saddle point happen. I'm going to try that same function again and maybe get a better looking answer. So it's going to be 3 take away x to the 4. Plus 2x squared else minus y squared. Click out of that. There we go. That's pretty much the same as the other one. Can you see this point here would be my saddle point? From this orientation, that definitely is a minimum. There, can you see it? It's a maximum. So it's both max and min. Doesn't it depend on what you're looking at? Another analogy. Can you imagine this was a funny shaped terrain? If I was at the point here, wouldn't I be able to look left and right and say, oh, I'm at the bottom of a valley? But from a different orientation, couldn't I look left and right and say, hey, I'm at the top of a hill? Right? So forward and back, you're in a valley, left and right, you're in a hill. You're actually both at the same time. And so when you are looking at solving these local max and min questions, you're expected to do it algebraically. Do not go immediately to GeoBra and put the thing in and say, oh yeah, 2 local max and a saddle point, done it. Right? Just using the graph. You'll know the location of them because I'm assuming that you had to do that part. Remember solving dz by dx and equals dz by dy is 0. So you know where to look, right? 2 or 3 critical numbers. But don't go here and say max, saddle point, max. You need to do it by math. And so don't take shortcuts like that because we want you to understand how you can prove something like that. And I am now going to, whoops, go over and start one, if I can. So let's look at, let's look at a simple example. Suppose you have this function and you're being asked quite straightforward, find the local max, local min and saddle points. Okay? Local max, local min and saddle points. And the function, if it's got any, because they don't have to have all 3, they might only have 1. For the most part, we tend to do these questions using polynomials, right? Powers of x's and y's. And just because the math is very messy otherwise. So step 1 is going to be find the critical numbers. Which we call CN for short, right? Well, you do the partial derivative with respect to x, and this guy gets you 2x, and this guy gets you y, and you get nothing out of that, and you make it 0. And at the same time, you find the partial derivative with respect to y. That gets you nothing. This guy gets you x. This guy gets you 2y, and that guy gets you 5. And we make it 0, and I'm going to call this equation 1 and this equation 2. And essentially, don't we need to solve, almost always, a system of equations? So you've got two equations, both equaling 0, involving x and y. Do you recognize this particular situation? You would have probably met it in 94, maybe 99. Can you remember trying to solve a system of equations? Oh, just give the name away. It's a system of equations.
I was about to.
Yeah. Yes, Travis?
Oh, no, I was just about to say is linear algebra. I was just doing them.
Yeah, just doing them. Okay, so what you need to do here is there are two techniques. One is substitution technique and the other is the addition method. I am going to choose the substitution method just because I want to. So I'm going to take equation 1 and I'm going to rearrange it. And when I rearrange it, y is equal to negative 2x. I'm going to take equation 2 now, and I'm going to replace this y with negative 2x. So I now have x plus 2 lots of negative 2x plus 5 equals 0. And that is x take away 4x plus 5 equals 0. That's negative 3x equals negative 5. As long as you do it to both sides, it's okay rule. So I'm subtracting negative 5 here. And that, with a little bit of a division, you get 5/3. So the solution to this, or at least partial solution to this, is that x equals 5. And then you use the fact that y is negative 2x to find this guy. So in this particular question, there is only one critical number, and it happens to have coordinates 5/3, negative 10/3. Now, I did all of that without sketching or looking at software and finding out that that guy there, right, has a hill or a valley, or it could be a saddle point. We don't really know yet. But I now know where to look, right? In this case, there's only one critical number, so there can only be one local max, min, or saddle point, right? There isn't 2 or 3 to find. That's step 1 done. Step 2. We're going to find this guy called D, the discriminant guy. Now, to get that guy, don't I need to find second derivatives of various kinds? And I will evaluate them at this point. So here goes. The partial derivative with respect to x was 2x plus y. So this guy will be 2. The partial derivative of y was x plus 2y plus 5. So that guy is 2. This guy is him. So won't this guy be 1? In this particular example, do you notice that all of these things happen to be fixed numbers? And in general, all 3 of these are probably going to have x's and y's in them. That's more typical. And when they do have x's and y's in them, won't I replace the x as 5/3 and the y with negative 10/3 so that I can find out what numbers these are? Because I do need to know what these are as numbers. In this particular case, they ended up being numbers, so I guess I didn't have that step. But in general, can you imagine that's going to be x squared plus y, 2xy, and whatever, right? Now, the value of D is the second derivative x, the second derivative y, take away this guy squared, which is 3, which, by the way, is positive, right? Now, what do I know about the value of the second derivative? Well, it's also 2, which is also positive. In my list over here, if the second derivative is positive and d is positive, then we are looking at a local minimum. And that local minimum, oops, happens at this coordinate. Now we have step 3. You're very often asked to find the value of it. In other words, how high up or how low down is this local minimum? Which means you are going to find the value of the function at 5/3, -10/3. So you are going to find 5/3 squared plus 5/3 times what? -10/3 plus -10/3 squared plus 5 lots of -10/3. Oh, that was tight. I should move over here. 25/9. Take away 50/9. Add 100/9. What's that? 50/3. So that's 150/9. 125 leaves 25. I believe it's -75/9. So the value of the local minimum is -75/9.
I think the 150.
A lot of work in that process. Whoops. Which one do you think I screwed up?
I think it's the last term. I think it's 50. Wait,
it's 50/3, isn't it?
Never mind. I'm sorry. I think
No,
you're right.
it's okay, Lindsay. I'd rather you do it. It's -50/3, but I just converted into 9 so it can join the others.
I see.
But it's worth checking.
Yeah,
Not a problem. Yeah, you keep doing that. It's safer than to let some slide. Okay, are we comfortable with that process now? Well, I'm surprised. I think you need 3 or 4 more, but that's good. At least you know how the process is going to work, right? It's going to be very long. This is, believe it or not, the shortest one, where there's only one solution to go looking. So say hi, everybody, and I will see you all tomorrow, where we get to do more and more of these guys. I'm just going to leave this guy up while I talk. So that if you haven't copied this, you only need to go to the video and scroll right to the end, and that way you can pause on that and write down the details. Okay.
Thank
So
you,
I
Professor.
think
See you
that's-
tomorrow.
Yeah, well,